Yeah, this is where we were. Yeah, good afternoon. So the morning we were talking about interpenetration. That's where we stopped it. Now we are going to see lots of application in different field. Okay, that will show the true multidisciplinary nature of these materials. The first thing comes from the porosity, the porous nature of this coordination polymer. Some people like Hiragawa calls it as PCPs, whereas Yagi calls it as MOFs. Okay, that's fine. We call it MOF. So that's it. So porosity is important problem. Whenever you think of MOF, of course, it's the three-dimensional or multi-dimensional structures, but usually porosity is the one that comes to our mind because it has got a lot of applications or potential applications. That's what everybody's working on. Porosity means it has got a lot of porous, vacant, empty spots, empty space that can be used for this purpose, depending on how big is the pore or the empty spaces for storing gas and liquids. That's the one. Second one, for separation based on the size. And ion exchange, we can change ions and so that we can purify. Cleaning of oil spill, you just put the mouth, it absorbs all the oil. When it can separate different gases and different compounds, isomers, why not? Heterogeneous catalysis. So catalysis can be done using this. Of course, sensing, nano reactors, and for drug delivery. I think I'm going to touch upon most of it. I may leave one or two. So usually nature doesn't like voids. It will be filled with something. If not, at least with gases. If not with gases, in this case, liquids. The solvent that we use. So, and also we have seen that in some cases we get interpenetration to reduce the emptiness. And Omari Yagi is credited for developing this particular field. Actually, he's waiting to receive his Nobel Prize. Last year, he was a potential candidate every year, but anyway, unfortunately, he didn't receive. So maybe in subsequent years, he and Kitagawa should receive it. According to him, he defined, in the 80s, 90s and 2000, there's a big war going on between Robson's group and this one. It should be called coordination polymer, or no, it should be called as MOF. And he redefined in one of his papers. Okay, we define the MOF as a three-dimensional coordination polymers that constituted metal ions such as this, use dicarboxylate linkers, and have been classified. But now it becomes a general phenomenon. Okay, anything whether you have pore or not, not to have it, but still you call it MOFs. Okay. So if you want to hear some of the lectures, I've given link every now and then, in your notes. Whenever you have time, take a look at it. They're very interesting. There are lots of YouTube videos. Listen to it. Usually, I play them in the class, but when you have full-fledged class, but now I don't have. So I'm going to play it in the best. Of course, there are many ways of making use of this time. There are many names. There are many names apart from PCPs and MOFs. MOBs, and I'm not going to acronyms and expand it. Okay, many people, whoever developed, they have their own names: PCNs, ZIPs, MOFs, MORPHs. Even for example, MOPs we developed. We have a reason for it because it's metal organopolymeric framework, because we put organic polymer into the MOF. So that's why we want to differentiate. Like that, there are so many. But whichever university they are working on, they started calling HKUST. Incidentally, HKUST1 was published along the line of Yagi, I think in 1999 or something. It is very popular, very famous. And that's the only one. They call it HKUST1. That's the only MOF that was made. The guy who made it, after his PhD, he joined as a lecturer in NUS, and he's still a lecturer. He's a close friend of mine. So, and this is a very famous one. And UIO, Illinois and Mill, USM, and a lot of SMU, NUS, even NU, Northwestern University. For example, Omar Farha is very, very, big guy in this particular field. He crossed MOF 1000. MOF 1000, he made it. The postdoc who made it, I met her in Korea about 2 months ago. We talked about Omar Farhai's character and everything. I met him actually. He's my friend also. Okay, now we need to classify. Every time every time you talk about something, immediately you go and classify. Coordination polymer. Okay, we classify. So here also we classify based on what Kitagawa says. He says first generation, second generation, third generation. The reason is all these porous coordination polymers, they have solvent. Once you remove the solvent, what happens to it? In the case of first generation, once you remove the solvent, the whole thing, the whole framework collapses. It is not just single crystal. Of course, you have single crystal. And if you remove the solvent, the single crystal collapses. And also, if you record the powder pattern, the same powder pattern that you simulate from the single crystal is not retained. It's amorphous. So you know that something happened to it. Completely, it is destroyed. Okay. So that is recoverable. No, this is soft crystal. It's type 3, type 1. Okay, collapsing. Collapses when guest is removed, but when you put the guest back, so it goes back. That's type 1. Second generation, robust and stable. The framework are maintained. That means nothing happened to the framework. The single crystal may destroy. Once you remove it, it may not maintain. But if you record the powder pattern, it will happen. So you can recover. You can just put back and everything. So it is retained. There's a third generation. It is stable, but dynamic and flexible. This is more interesting. Many people started working. This third generation, here, the structure might change when you remove the solvent. And something else guest may also occupy, and that may change the structure. It's called type 3 structure, third generation, which is rise in the literature. That means more and more, third generation MOFs have been discovered. They call soft crystals. Okay. So we talk about soft crystals, the collapsed framework. Okay. So this is first generation, second generation, third generation, and the third generation can further be classified into guest-induced transformation, recoverable collapsing, and guest-induced reformation. Okay, in this case, it collapsed. Second generation, it retained. The third generation, it goes back. And here also guest-induced, then some guest will go into it, and then that will change. And reformation, completely, it will be changed. Kitagawa has been working on a lot of gas option. So he is able to determine the crystal structure when the gas is passing through the pores. So still single crystal is retained. So he measured the structure as he pauses under different pressure. That's how he looked at the crystal structure. He found that it is changing. Okay, that's how he found out that gas-induced reformation and everything still it maintains its crystal structure. So. Credit goes to him because of his classification. He has done lots of work and still working. He's, I think, 72 or 73, still working. I met him again a couple of months ago in Japan. Ferre is the one who could have won Nobel Prize, but he passed away. And he was a big competitor for Yagi. They used to fight, and unfortunately, he passed away, and his senior, junior student or postdoc, Christian Serre, took over. Now he's a very famous guy. And he classified the type of structural changes, okay, how it can happen, the structural changes. In the case of 1D, it can bend. By bending, the structural change can occur. No, not in terms of single crystal, but in the structure. If you take a look at the X-ray pattern, X-ray data after and before bending, there'll be a change. If it's a 2D, this goes like this. It breathes out, and you get a lot of, the distance increases and decreases, or it can slide also because of this. Okay, it can slide, or it can increase straight away. Or when you have a 3D, when you have spring-like thing, it can compress, or it can go in different ways. So things are happening. We can see it in mechanical way, but this is really happening in the molecular structure, especially in morph structures. When you determine the structures using single crystal X-ray crystallography. There are other types of structural dynamics. This one by Makoto, again, Tokyo University. And when Birada from IIT Kharagpur is the one who was a postdoc at the time. He showed that he made them, Birada made a 2D morph with nickel, with L is nothing but this long spacer ligand. Okay, and he has got xylene. The xylene was incorporated into this. And he looked, the porosity was not really great. Okay, but that's nothing to do. Okay, because the way the pink one is the first layer, this one is the second layer, and if there's a large space that has been occupied, that's obstructed by the second layer. The third layer will be superimposed onto the red one. So in between, you have got xylene. When you take the single crystals, when you put it in a solution that contains xylene, xylene molecule by, what is it? Instead of xylene, I think, what is it? Mesitylene, 135, methyl compound. So if you put it in, xylene will be replaced by mesitylene. Mesitylene is bigger in size. Because of that, it slides. It slides and occupies the space. So there's a complete sliding of this taking place in a single crystal to single crystal manner. You take this compound and then putting it in mesitylene, it goes to this. When you take this and putting it, it goes back. You can confirm it by X-ray crystallography. This is the dynamic, structural dynamics. This is quite interesting, but there's no bond breaking or bond making. It's just sliding of the 2D structures. Okay. Now, pore size. Pore size is very important for any research and any potential application. So let's classify the pore size here. Usually we'll see ultra micro pore size. That is about 5 angstroms or less. Normally we see them in normal complexes or other compounds, even in organic or inorganic. But micropore, the size is about 5 to 20. Mesopore is 20 to 500. Macropore is more than 500 or 50 nanometers. You can divide by 10, becomes nanometer. For example, MCM41, mobile composition of matter, MC141, there's the number 41 time. The mesoporous, they prepare the mesoporous, this compound, and it has got 2 to 6.5 nanometer. So for everything about before MOF, they were using it, zeolite. This zeolite, they have been widely used for a lot of applications, real applications, as catalytic cracking. The synthesis is given here. Don't worry about it because it's easy to make it, and they can vary the pore size and everything. So this is what we want to know. Based on what we want, what kind of pore size we want, then you go back and design what kind of metal, what kind of the spacer ligand you want, and then you go and make it accordingly, and then look for those applications. That's what we need to do. So how to control the size and shape of the pores? We are going to talk about it. The major goal in design, that's a one. Neutral frameworks are advantageous because in all these things you don't want anions and cations. They will also occupy the cavity, and also you'll have problems. And many other uses. Okay, of course you need anions and cations, anionic caging, cationic frameworks. But in this case, if you want gas option and other things, you don't want extra thing. So it's be neutral. Coordinating anions will occupy pores. Increase in pore size. Okay, that we know. We just discussed. Increase in the length of the spacer ligand. But we also have a problem. If you increase the length of the spacer ligand, it can also interpenetrate. That can reduce the pore size. But many people have succeeded. I'm going to talk about it. Maybe next slide or after that. An example is shown here, shown in one of the slides later. But generally, how do you control? Again, we have to go to Omariagi's work, isoreticular MOFs. He call it isoreticular MOFs. Without changing the interpenetration, he can increase the pore size. How do you do that? So from BDC, you put in some substituents. Okay, at the same time, he increases. Because he increases with substitution, what happened? The pore size increases. It's again in all these things only a twofold interpenetration, nothing else. The interpenetration is constant, but there is no additional interpenetration. How it is possible? It is possible because of the use of the cluster. Cluster, like if had used metal ion, one metal ion, it's not going to. That's according to him, because of the cluster nature of the node that prevents any interpenetration. That becomes really big. Secondly, he started using some additional things as substitution. That will also prevent any further interpenetration. Because if it has to interpenetrate, a similar type of ligand should go in, because he will make sure that that's eliminated. So by using his isoreticular MOFs, one can reduce, or one can control, reduce the interpenetration and control the size, or increase the size gradually. That's what he has shown. From BDC, the small size up to, I'm going to show you this exact size, how big one can do it in the next slide. Okay. Large pore, maybe in some other place. Okay, the next one, he made non-interpenetrating, and that was published in Science a couple of years ago. He started making this type of pores, non-interpenetrating, right, from 10 angstrom diameter up to 85, 85 angstrom, and then, he made it non-interpenetrating up to 98. You look at his ligand, if you can make this kind of ligand, of course you can, but can you make it? But he has got a big team who can make this kind of thing. According to him, the biggest ERMOF 74 1X, 9 that he made, he claims that he can put a small protein inside. Okay, that's why he was able to make a series of MOFs and controlling the size with the nature of the ligand. Okay, this is one of the success of Yagi. Okay, and of course, if you have interpenetration, I already told you the answer, how to control the interpenetration. There are two ways you can do. Instead of using metal ion, you can use a big cluster ion as the node. Okay, I mean he used what is it? This one. Z4O kind of thing. So, one can also use, many nodes and different clusters, in fact, for making, to avoid the interpenetration. People have succeeded. Okay, there's a lot of literature available. The other way, this is another way, and we are going to see later. You make a MOF with a large side chain. Okay, that will occupy the empty space. Because of that, I mean, you also have a ligand here. You also have a ligand here, everywhere. because this bulky substitution will occupy everything that will prevent any interpenetration. What he does, he removes this by heating it. Okay, the whole tertiary butyric acid can be removed by. Then by removing this, he creates a lot of voids. So that's a tricky way. That's another way. This is what is called PSM, post-synthetic modification. Okay. So this is the way you can avoid interpenetration. This is what I was about. I was talking about in the next slide. It's not the next slide. This is by the Wenbin Lin. Now he is in Chicago. He used this kind of ligands. It's a binaphthol, right? Binaphthol. I don't know what is it. Naphthol, right? So this is probably, you guys, if you're doing catalysis, immediately you know that how useful this is. So he used this ligand. He made MOFs. Okay, he made MOFs. All are non-interpenetrated, for connecting and nicely forming. He was able to control the size of the pore, and you have got OH inside. He was trying to put in all kinds of titanium butoxide or something, and then he was doing a lot of catalytic activities inside. So that's a way you can. I think my slides is not updated here. That's why I tried to write something here. Anyway, I don't know. Never mind. So you can use this. This is a method to introduce catalytic centers into MOFs. And again, this is another PSM method. You can make it only with this, and then once you made it, then you can replace this OH by reacting with titanium isopropoxide, and then it's ready for catalytic activities. And you see the difference in catalytic activities in the because of the different the size of the pores. You can see differences in different MOFs. What else you can do? Gas option and storage. Okay, you can different gases. What do you require? What do you need for gas storage and gas option? So you need porous specific surface area, because you need your gas to be absorbed on the surface of the MOF surfaces. Conventional zeolites will have about 500 square meters per gram. On the other hand, if you have MOFs and that has got a range of from 1,000 to 6,000 meters square per gram surface area, so you can make it. That can be used to trap a lot of gases. I mean, I just mentioned few, but you can do a lot. How can you compare the porous area, the surface area in the porous MOF, with the real outside world? See, when you have 1 gram of the MOF, okay, with 10,000 meters square per gram surface area, that is equivalent to a soccer field. So you will see that how big it is. So we have that much surface area, and all the gases can be absorbed. That's what you have in 1 gram. So importance is energy storage. You can use it for energy storage, capture of CO2 emissions, and cooking. For example, cooking gas cylinder. You know how safe it is because of the gas inside, propane gas. If you put in the MOF that absorbs, you can put in large quantity, and also the safety will improve. Same thing with hydrogen storage. Okay, it's very difficult nowadays. People are pushing for hydrogen vehicles. Liquid hydrogen. You need to store it. It's heavy. And still, of course, they are trying to do it. I'm not sure what is inside, but according to if you have some MOF that can absorb hydrogen, if you put it in, is going to absorb more under very high pressure. So that means, instead of putting it, let's say 10 kilograms, you can put in 100 kilograms because it can absorb more. So these are the advantages. The ultimate goal, of initially by Yagi and everybody, and whoever jumps into this MOFs to do the absorption, they want to, have hydrogen absorbs at room temperature and close to ambient pressure. If it can absorb, then, if you can make it in the lab, you quit on the next day, go on, start your own, company, you'll be a billionaire in no time. Okay, so the MOF, okay, 177 CO2 absorption, for example. If you have a MOF of this, I don't know how much it is. Okay, I forgot to put it in. 177, if you put it, that's equivalent to 9 cylinders. Maybe one, I'm not sure how many, maybe 1 kilo, I don't know. So equivalent to 9 cylinders. That means you save a lot of space. Also, that's, and also the pressure wise, it is very safe to handle. Again, if you are interested more in this, you can watch these 2 videos. Hydrogen bond, hydrogen binding. If you're working on hydrogen's absorption, you have to worry how hydrogen can interact with the surface inside the MOF. There are 2 ways. One is physisorption. The other one is chemisorption. Chemisorption means it's, literally reacting and forming, hydride forming to the metal. That's going to be a problem. But, removal, maybe forming may be easier, removal may be difficult. You need to heat it up to very high temperature. So we have to go for physisorption. That's the only way. The large surface area favors maximum H2 uptake. Whereas you have got 1 or 2 in the corner and very difficult to do absorption. We always think that interpenetration decreases absorption of gases. No, actually it improves physisorption. You'll be wondering how. It is not the empty space that is responsible. You would see that from the experiments, doubly interpenetrated this MOF found to absorb 1.9% weight of hydrogen at 1 bar at 77. It shows 0.6% improvement over non-interpenetrated compound. So interpenetrated compound shows higher absorption. That shows that, it's not the empty void space that is responsible. Okay. Why? You may, I'm going to talk about QST. Okay, then you will know why, what is it all about, whether it is interpenetration in next one. The other one about CO2 absorption. CO2 absorption is also very important environmentally because you want to remove CO2 from the environment, and then you want to save it or convert it into any useful organic compound or store it somewhere. And this is the easier way to remove it using MOFs. And this particular one, this particular MOF is zinc, BTB is benzene tribenzoate compound. It shows very high uptake of CO2. This compound shows high surface area. By the way, there are 2 different ways of measuring the surface area. One is Longboard and the other one is BAT. Of those, BAT is more useful for MOFs. But although I'm saying all these things, and it's better, many of them reports both Longmuir as well as BAT. He said exceeded the capacities of zeolites and activated carbons. That's why I put it in. Is much better than what is available currently. The other one, whenever we think of CO2 absorption, the work of Chen Xiaomin comes into our mind. He is the first one. He made metal azolite framework structure. Xiaoming Chen from Sanyata University. Metal azolite. He used to be a frequent visitor to India, but not nowadays, I guess. And what he called as metal azolate, he used, this kind of what we call zip imidazole based one. He called it azolate and imidazole. Yagi changed it into zips. Okay, zips is quite popular now, not azolate. So metal, he called it zips means, this is zeolitic imidazole framework type of structure that shows high thermal chemical stabilities. That's a reason why, and also exceptional selective uptake of CO2 in the presence of everything. So whenever you think about CO2, zips are quite popular. Now the problem is this was developed, just before all of this metal azolate. He has done lots of work, but our Yagi, because of zip work, he stole the whole show. He's not getting any credit, and he started complaining about it. Anyway, so these materials are also useful for gas option and then storage. Okay. I think did I? No, I didn't have. I didn't. You're not. I think you haven't uploaded the recent ones anyway. That has got more. Anyway, never mind.
I have. I can say
it's okay. Never mind. I can do it without making the break. Can do it. All right. Now, so how do we measure it? How do we measure the? How the gases adhere on the surface? What do you call it? Isosteric enthalpy of absorption. It's what we say QST. QST, I'm showing you, this is the experimental plot. What we do, this is isosteric heat. When gas absorbed to the surface, because of the interaction with the surface, energy is released. That is isosteric heat. And they measure it along the distance. Okay, how much amount of things absorbed. That means, once you complete the layer of the gas, the second layer has to absorb on the surface, which is CO2 or hydrogen is already there as a second layer. That's the reason, once the layer, on the surface area has been consumed, it's very difficult for the gases further adhere to the surface. It has to adhere to the gas layer. Okay, that's a problem. That's why the pore size doesn't matter whether if it is interpenetrated. You've got another surface that is closer to it, so the gas can absorb to that. So that's not the issue. That's the reason. So this is if you look at the amount here, naturally, I don't know if you have a surface area, you'll find out that you'll have a second, third, not more than 4 layers you can have it. So naturally, even if you have a single layer, in order for the gas to be completely filled, it's going to be difficult. That's why the QST will decrease. If it is not decreasing, that's a good sign. So usually, if you have 30, 40 around this value, is wonderful. That means QST over absorbed CO2 doesn't decrease. That's a wonderful news. So this is what they're looking for. Whenever you want to publish a paper on absorption, immediately they will ask you, do you have QST? Okay, let's talk about ultra high porosity. What is ultra high porosity? How big? How yeah, that's the one I was looking for. Anyway, so it is there. How ultra you can make it? This is the MOF that Yagi made it with 2 different types of carboxylate acids. Carboxylates, he calls it as MOF 210. This is the repeating unit of the thing using this SBU. The total carbon dioxide storage capacity is, according to him, is 2.8 grams per gram of it. That's 3 times more it can absorb. Okay, now let's take a look at this table. The table will give you quite interesting result. He compares different MOFs that he made with, and also others. And he had given the crystal density. Crystal density after he removed the solvent. Okay, not because we know that in all the MOFs, you will have lots of solvents. So when you have solvents, you can't do sorption. You have to remove the solvents first, and then you have to activate it in the absence of air in vacuum, and then you allow the gas to go. It will go and absorb. Then you measure it. Okay. When you do that, you can really calculate the crystal density. What's the density of water? Once, right? Look at the density after you remove the solvent here. 0.44. It's up to 0.22 here of 200. So if you have desolvated MOF, it will float in the air. It will float literally. Okay. But the problem is because it's it cannot retain the vacuum, the empty space. It will be filled with maybe water from the atmosphere. Okay, so the density is bound to increase anyway, but still. PET, look at the area, 4,000, 5,000, all in thousands. Okay, but this is what quite interesting. This particular MOF, in BBC, the density is 0.126. This is the lowest density after you remove the solvent, which has got 94% porosity, 94% porosity, MOF 399. Here also look at the void. See, empty space. Of course, that is filled with solvent, but that is available for gas option and other things. See, 83%, 90%, 90% is empty. Just like cigarette or matchbox, nothing. Open that box. There's nothing inside. Okay, you fill with water and then you have a bucket full of water. You just throw water and it's ready. Something like that. Okay, 90% empty. And those things are unimaginable. Now you can make it. You can use it for various purposes. Okay, I don't want to go further into it. So that you can talk about separation. You can talk about other absorption of and how isomers can be separated. As the literature is quite very, very vast, and there's no point in talking about it. So this is the basic thing that you, as long as you can read any of the literature on gas storage, in different journals. And let's move on to some other interesting aspects of MOF chemistry. It's called post-synthetic modification. This particular one will be very useful for heterogeneous catalysis for many other reasons. Okay, not just heterogeneous, so many reasons. Let me tell you how and why. So you make a MOF. Okay, make a MOF. This is the metal. It can be metal cluster. This is your ligand with a side, functional group. This is a spacer ligand with a functional group. Then you make it. You made the MOF. The functional groups are there. Assume that this is BDC with NH2. So that is there. Then you modify that once you made it. So that's what happened. Seth Cohen was the first one, to show that this works well in a single crystal to single crystal way. He made the amino derivative, that is the MOF3, and then once he made it, it's a single crystal. The structure is shown here, and then he reacted this amino group with acetic anhydride, right? And in CaCl3, if he does it, then acetic acid is removed, and this is acetylated completely. So the product he got is also single crystal. So the pore is occupied, is actually, it's not NH2 anymore. It's completely derivatized to this. So this gives a lot of ideas. At the time he did it about 20 years, 15 years ago. It was a very, very popular one. And once you know you can do it, then people started jumping into it and then modify the pore. And then with, as I mentioned to you, titanium and all the other things, and then make it a heterogeneous catalyst. And then once you make this kind of derivatives, then you can do all kinds of catalysis. That's an interesting thing. But you can do with other, not necessarily titanium. There are a lot of other metal complexes that can, homogeneous catalysis that that you can put it there very easily. So that is the main advantage of this PSM method. Not only that, okay, you can derivatize, or you can derivatize the site functional group that is present in the ligand. You can change many things. Okay, this Omar Farha, who made it 1,000 MOFs, synthesized 1,000 MOFs. He calls this one as post-synthetic exchange, PSE. Okay. If you have a MOF, this is a ligand, this is a metal. Here you also have another metal. You can do metal exchange, and preferentially you can just change one in the middle to another metal, and you can also do it at the node. You can completely change. This can be, for example, cadmium, and this one silver. You can completely change it. Whatever, or palladium, whatever, you can completely change it. Or if you have bipyridyl, you can put longer spacer. You can make, completely convert it into another MOF. From one MOF, you can convert into another MOF. Nowadays, hundreds of papers are available. This kind of thing. Sometimes you are not able to synthesize a copper compound, but you can synthesize a zinc compound. Then you can exchange. There are ways, that they have given in this, copper can be exchanged or zinc can be exchanged, by the cobalt and all these things. So play the trick, and then you get what you wanted. So many times you can't make, one particular metal. Then using this method, you can definitely make these things through indirect way. One example is shown here. How ligand can be modified. You see here, he made this MOF, and he also says that this is sale method. This is again he use ligand exchange method. You can change all these things from. So he changed it to this derivatives using SALE, SALE, and then side vinyl group, and then metathesis. He's completely converted into cyclized, and completely another MOF. Sometimes you cannot make, if you come back to this, sometimes if you have a bulky group here, if you try to make the MOF directly with this ligand, it may not be possible. So you have to use indirect way of making this type of thing. And also you modify the pore size. If the pore is, it's NH2, you have acetylated one, that means the pore size and shape is changed. So that can be used for various other reasons. Okay. What are the advantages and disadvantages of, I shouldn't say the disadvantages. What are the characteristics of this? So you can, this porous frameworks are stable. It has to be stable after removal of gas. That is very important. That's number one. If you want to do PSM for your catalytic activities, you want to make sure that the framework is stable after you remove the solvent. And you can very easily, do the EXRD and confirm it. And also the space inside can be used as a reaction vessel. That means a size. If you want to take one molecule, the molecule size that you plan to do should be smaller than the space available. So make sure that the space inside is big enough to accommodate your reaction. Ligands inside inside the surface of the MOFs are also exposed to and accessible. This is very important. Whenever you try to do a reaction, make sure that it is in the channel, the empty space. It's projecting along the empty space. Then you can very easily modify. If it is very well, inside the MOF, which is not exposed to the channels, then it's very difficult to access this. And you can derivatize without affecting the overall framework and or the integrity of the structure. That's very important. Okay, I want to make, I want to make a nitro derivative. I want to put a nitric acid and then I want to boil it. You destroy the whole MOF. You need to make sure that it is possible to derivatize the functional group without affecting the overall. So you need to use milder reagents for sure, not very harsh reagents that will destroy the structure. So you don't have to change. By doing so, what is the advantage? You don't change the topology. You keep the same framework, and then you know what you are doing. Okay, you can measure the size, you can measure the shape inside of the empty space, and then based on that, you do any kind of reaction or catalysis, you may be able to explain what is really happening in the mechanism without any problem. And also, of course, you can fine tune and optimize the size and shape for some other reasons. But yeah, and also the pore size should allow all these reagents to go. These are the things you need to think before you do PSM, which is not that difficult. Okay, it's not that difficult. So he's written so many reviews. I didn't follow after this. I think he moved away from this, from Cohen, all Cohen's reviews. All right, now. So far, what we have done, we learned about different topologies, of course, supramolecular isomerism, interpenetration, how to control the pore size, gas option. We also see that this post-synthetic modification is useful for a lot of many things for chemists, material chemists, and other people. Other applications I'm going to talk about. See what other things you can do apart from gas option. But so far we have said because it's an empty space, you can use it for gas storage and exchange and that kind of thing. What other things you can do? What other applications using this physical and chemical properties of this compound? So this is what everybody started asking questions. And then I'm going to talk about the applications in various fields, including magnetism, optics, and so on. Okay, let me go and touch upon. But I haven't covered this. I think I mentioned to you separation of gases and catalytic properties. Right. I think I'll take a break here, maybe 5-10 minutes, and then start because I need to change the slide. Yeah. I realize that I didn't change the slide. Okay. I'm going to talk about the molecular magnets and how MOFs can be used as in magnet, for various applications in using magnetic properties. Okay, that's what I'm going to say.